Okay, we're moving on to a new kind of approximation. This is where the situation calls for a binomial distribution, but instead of using a Poisson approximation, we're going to use a normal distribution. Okay, now this will have been explained why in class this works, but all the theory we need is in this box. So we need n to be large again, but unlike a Poisson, we need a p. Instead of a small p, we need a p that's not too close to 1 or 0. Okay, and in fact, if it's anywhere between 0.1 and 0.9, that's usually fine. Okay, sometimes it can even be closer to 1 or 0. So we don't have to be massively far away from 1 or 0, but we have to be not too close. All right, so if the original distribution is, then we can work out its mean and its variance and therefore its standard deviation. Okay, and the normal distribution we set up obviously should have a mean that agrees with this mean and a standard deviation, a variance that agrees with this variance and a standard deviation that agrees with this standard deviation. Okay, but there's one key extra step here, which is called the continuity correction, which means that we have to adjust for the fact that the binomial outcomes can only be whole numbers, but for normals we can have everything in between the whole numbers as well, which means we have to adjust the probability. So I'm going to show you how that works with some examples. All right, so in this question we've got a binomial, we've got an n of 40 and we've got a p of 0.2, and n is pretty large and p is 0.2, so it's not too close to 0 and it's not too close to 1. So therefore a distribution that can be used to approximate x is a normal distribution. So using the word normal is nice, but of course we can say that our distribution is that it's approximately true that x twiddles a normal with a mean and a sigma squared. Remember, when we set up a normal, we use the variance here. So our mean has to come from our binomial. So our mean, the formula for the mean of a binomial is np. So our n times our p is 40 times our 0.2, which is 4. No, it's not, it's 8. And our variance is our np1 minus p. So we are going to be doing 40 times 0.2 times 1 minus 0.2, which is 0.8. So that's going to be 6.4. Okay, so I've got a nice mean and a variance. Okay, so I fill them in. So 8 and 6.4 is the answer to part A. That's fine. All right, part B. Okay, part B is just saying, okay, let's not work out any probabilities yet. Let's think about what we'd have to do for the probability of x being less than 6. Okay, so for a binomial, if you were going to use this on your calculator, you'd have to do this. You'd have to say a binomial could be 0. The values we're interested in near 6 are 5, 6, 7. It could be anything up to maximum one for this is 40. Okay, all right, so ticks and crosses. So it's got to be less than 6. So it could be 5, it can't be 6 or 7 or 40. It can be 0. So, okay, if we're doing the binomial, we would do the big box and the little box. Well, actually here, we only need a big box. Those are the probabilities we want. Okay, so you just look up 5 because binomial calculator works with the probability of it being less than or equal to this value. But remember, with a normal distribution, okay, then all these values between 5 and 6 would be in the question. That'd be possible values. So our cutoff line that we've drawn here between the 5 and the 6 is not at 5, it's not at 6, it's between. And if for the continuity correction, we assume it's halfway in between. So this cutoff point is 5.5. So the probability of x being less than 6, okay, turns into the probability of x being less than or equal to 5.5, okay? Or you can put less than 5.5. Now we've done the continuity correction. For a normal distribution, remember, the probability of being exactly 5.5 is 0, so it doesn't matter whether you use a less than or equal to or a less than sign there. But our 5.5 does need to take account of the fact that our binomial box was between the 5 and the 6. Okay, so that was B part 1. Okay, B part 2, okay, is going to be for the probability of x being less than or equal to 8. All right, so we have all values from 0 to 40, but we're interested mainly in 7, 8, 9, to 40, ticks and crosses. So now it's less than or equal to 8. So it can be 8, it can be 7, it can be 0, it can't be 9, it can't be 40. So our box would be like this. We only need the one box. For our binomial calculator method, we'd be considering our box there. But now we've drawn it, we can see that between 8 and 9, the cutoff is 8.5. So the probability of x being less than or equal to 8, as stated in the question, turns into the probability of x being less than or equal to, doesn't matter whether it's less than or equal to, as we said just now, this cutoff value. So the continuity correction cutoff value is 8.5. Okay, so x being less than 5.5 for this one, x being less than or equal to 8.5 for this one. So I'd encourage you now to think about this one and this one. Okay, this one is going to have two cutoff values. All right, this one's just going to have one. All right, have a go at them by drawing the diagrams yourself. Pause the video. Okay, so you've paused, you've gone away. Okay, so now, okay, are you back? You've done that? Hope so. Okay, so if you've done it, part 3, what you should have done is this. You should have drawn your outcomes for part 3. So here they are, and we want to be greater than 10. So your ticks and crosses, you should have had greater than 10. These all get crosses, but these get ticks. So your two boxes would be, well, there'd be a box for everything, okay? But then there'd be a box that is everything greater than 10. So the cutoff is at 10.5. Okay, so the probability you'd actually need to work out from your normal is the probability of x being greater than 10.5. Or if you prefer, greater than or equal to 10.5. Once you're into a normal, it doesn't matter, but your continuity correction is 10.5. And for part 4, your list of outcomes looks like this. Okay, your ticks and crosses, we've got to be greater than or equal to 4, but we've got to be less than, but not including 7. So 7 gets a cross, these get crosses, these get crosses. So your big box and your little box, your big box would come up to there to include all the ticks. Your little box would come to there. So your cutoff values between 6 and 7, this is 6.5. Between 3 and 4, this is 3.5. So we've got cutoff values of 6.5 and 3.5, and the probability we want is that the probability of 3.5 being less than x being less than 6.5. That's the continuity correction. You could have less than or equal to's on these equal to's, but this time I'm not going to put them on because it doesn't matter for a normal. Okay, so that's part B. Now for part C, now we've done that, part C is just about doing bog standard normal distribution calculations. Okay, so we're going to have a z-score. Okay, for the first two we're less than that z-score. For this one we're greater than a z-score, and here we're between two z-scores. But this is now ordinary normal distribution calculations that you've been able to do since S1. So really I'd encourage you to do part C on a bit of rough paper, get your answers, and then we'll come back and do them properly together. So go away, pause the video. Okay, don't come back till you've done them. Okay, so you've gone away. Good. Okay, and now you're back. You've done the distributions. Okay, so we're doing normal distribution probability. So for part 1, okay, we need a sketch. So we have got 0 in the middle, okay, but that is the mean. Okay, so in brackets our x value for the mean, the distribution we're using has got a mean of 8. Okay, and we want to use the value at 8.5, so we are less than or equal to the value at 8.5, because all we're doing is, oh no, it's not, it's talking rubbish, aren't I? I'm doing the second one or something. The first one we're doing 5.5. We want to be less than 5.5. So there's 5.5. I want to be less than that. So there's my picture. Okay. What's my z value? Well, my z formula is z equals x minus mu over sigma. Okay. All right. So hang on. Word of warning. We did the normal. We just set up the distribution with a mu and a sigma squared. But of course, for our probabilities, we need to know our sigma value. So if sigma squared is 6.4, don't forget you have to square root the variance to get the standard deviation. There are more opportunities now at A2 for mucking that up. Don't let it happen to you. Actually, I'm not going to bother to get a messy decimal for the square root of 6.4. It isn't a very nice number, but I can use square root of 6.4 in my formula. So my x value is 5.5 minus my mu value, the mean, is this 8. So that 5.5 should be in brackets, shouldn't it? Because it's an x value, not a z value. So 5.5 minus 8 over square root of 6.4, and because I'm on this side I'm expecting to see a negative value for z. So here's that calculation set up on the calculator, press equals, and we get, oh, it's negative, and it's minus 0.9882. So minus 0.9882 is my z value, and then to work out the probability I want, then I need to use the 5.5 as my upper value. So back onto the calculator, go into a different mode, normal CD2, lower is minus 99999, upper is our minus 0.999 minus 0.9882. Okay, and of course I'm using a z value, so I don't muck around with the mean and the standard deviation, and I get this probability of p equals 0.1615. Reality check. This is less than a half. The probability I want is clearly less than a half, so this has got a good chance of being right. Okay, so make sure you've got a nice clear version of that in your notes with the diagram. It's still compulsory to have diagrams for normal distribution questions, okay? And if you waited for me to show you that because you'd forgotten and you didn't work out the other ones, now they should ring bells, yeah? Work out the other three if you haven't already worked them out. Okay, part 2. Part 2, see part 2, we now want the probability of being less than 8.5. So our diagram's the same. It's still got 0 in the middle, brackets 8, okay? But now we want the probability of being less than a bracket of 8.5. So our z calculation is 8.5 minus 8 over sigma. Sigma is not sigma squared. Sigma is root 6.4. And we get a z value of something positive, 0.1976. Here it is, and the diagram suggests that's sensible. We would expect a positive z, and then on normal distribution calculation mode, again we've got a lower value of minus 99999, but our upper value is now plus 1. Whatever we've just got, so 0.1976, giving us a probability of p equals 0.57832. So that's part 2, and then for part 3 I'm going to squeeze part 3 in here. Okay, part 3, we have got a diagram where we want to be greater than or equal to 10.5, so we've got still a 0 brackets 8 is the mean, is still 8, but now we want to be greater than 10.5. 10.5 in brackets is over here, and we want to be greater than that, so I'm expecting a positive z value, but I need to get a probability of less than a half. So my z value is going to be 10.5 minus the 8 over the square root of 6.4. So same kind of calculation we've been doing, and we get a z of 0.9882, which is what we'd expect is positive. So there it is. So I've got a positive z value, but now I've got to work out my p value from my calculator, and now this is going to be the lower value because I want a value above that one, so I'm going to use that as my lower, and as my upper I'm going to be having 9999. So if I type that in as my lower, 0.9882, and I type in my upper as 999999, ridiculously high, but there we go, and we get a probability of 0.1615. 0.1615. And in fact, if you've been alert, you might have noticed that 5.5 is exactly as far below the mean as 10.5 is it above it. So we've got two diagrams that are symmetrical, and because they're perfectly symmetrical and the shading's gone the other side as well, I've actually ended up with the same probability as the answer. I've given it to more decimal places here than here, but it's the same probability. Okay, and then for the last one, we've now got two z values to get. Okay, so our z values are going to come from, so the third one we set up, where's the continuity correction? Okay, so the original probability was being between 4 and 7, but of course I had to continuity correct those values, so then I have 3.5 and 6.5, so I have to work out the z values for those two. Now I've run out of space on this bit of paper, and you're supposed to have drawn this out fully anyway. So whatever you do, set this out properly. So for the last one, for C part 4, I'm not actually going to write out a solution. I'm going to change colour, because this isn't what I want your notes to look like. I want this to be written out properly in your notes with a diagram. Okay, but just so you can check your values, the Z value for the 3.5, you're going to get a Z value of minus 1.7788. And for your 6.5, you're going to get a Z value of minus 0.59293. Okay, and your diagram for these should look like, your means in the middle, these are both negative Z values, so it should look like this, but we're going to be using the lower one, the bigger negative one as the lower, and the other one as the upper, and you're going to get a p-value of your answer as 0.23897, so that's 90. Okay, so that bit in blue should not look like that. It should be done properly, just like the bits we did in red. And there's a further part of the question, because there's part D, justify the use of a distributional approximation in this question. Okay, so that's going back to the theory. We need to make a comment about n. Okay, what was n? Well, the n value we've been using is 40, so n equals 40. And that is large, okay? Anything more than about 30 counts as being large. And p, which was 0.2, well, for a Poisson approximation, it would have to be small, but I'll comment for a normal approximation that this is not close to 0 or 1. 0.2 is easily far enough away from 1 for a normal distribution approximation to be okay. So that's how you handle this question. So this, in fact, that's an adequate statement for why a normal distribution, normal approximation is justified. So we're done.